Allow me to introduce our panelists for today's webinar, Karam Siddiqui. Karam is a technical product specialist with Amphenol Communication Solutions, HSIO Connectors business unit. With over 7 years experience in the industry, Karam holds expertise in technical roles, product development, market research, and data analysis. Thank you for joining us today, Karam.
Thank you, Greta, for having me. Thank you, everyone, for joining. So, I'm from High-Speed I/O Connector Business Unit with Amphenol, and our today's topic is artificial intelligence and machine learning. So, artificial intelligence and machine learning are not just buzzwords. They are, in fact, transforming our industries and reshaping economies, even changing our day-to-day lives. So, what is artificial intelligence? So, artificial intelligence is a simulation of human intelligence in machines programmed to think and learn. And machine learning is a subset of artificial intelligence that focuses on the development of algorithms that allow computers to learn. So where does HSIO come into play with these artificial intelligence and machine learning? So for AI and ML, there is a lot of need for computing powers. So you need a lot of servers and racks. And Amphenol High-Speed I/O Connector Business Unit, we make the connectors on the front end of these servers that allow it to be connected to other servers on the rack. So there are different types of connectors that we have. So we have SFP form factor connector, we have QSFP, QDD, OSFP, and Mini-SAS HD. Later on in our presentation, I'll talk about 112 gig high-speed I/O connection development and also our thermal solutions that we have. So our division is spread out worldwide. We have 5 different R&D facilities. Our engineering is mainly done out of Valley Green and Toronto office. Our signal integrity is done from Nashua, New Hampshire, and our manufacturing is done from India and China. We launch 4 to 5 new products every year, and we have over 100 custom designs every year. We're leaders in MSA standard, multi-source agreement, and we have the shortest lead time in the market, which is 6 to 10 weeks. Here's a chart that shows all the different form factors and number of channels, data rate, and the maximum bandwidth per port. So SFP is single form factor pluggable, so it has one high-speed lane, and the SFP can do 2.5 gigabits per second per lane. So the way to calculate maximum bandwidth per port is by multiplying the number of channel by the data rate per channel. So 2.5 times the number of channel, which is 1, gives you 2.5 gigabits per second per port. So SFP Plus can do 6 gigabits per second, and then we have our Express port, which is able to do 16 gigabits per second per lane, and Ultra port can do 32 gigabits, Extreme port can do 112 gigabits per second per lane. Then we have our QSFP, which is our quad small form factor pluggable. So as the name suggests, it has 4 high-speed lanes, and it starts off with 10 gigabits per second. So an aggregate speed per port is 40 gigabits per second. Then our Express port can do 25 gigabits per second per lane with an aggregate of 100 gigabits per second. Our Ultra port, 56 gigabits per second with an aggregate of 224. And then our Extreme port, which can do 112 gigabits per second per lane with an aggregate of 448 gigabits per second per port. Then we have our Mini-SAS HD, which also has 4 ports at 32 gigabits per second. And then our QSFP-DD, which has 8 ports which is the double density version of QSFP. And this has an aggregate of 896 gigabits per second per port. And then we have OSFP with also 8 channels, 8 high-speed lanes, and can do 112 gigabits per second per lane with an aggregate of 896 gigabits per second per port. So starting off with SFP. So our small form factor pluggable has 1 high-speed lane, and it is backwards compatible with SFP Plus and SFP28 modules and transceivers. So we recommend matching the connector speed with the module speed to get the most optimum performance, but our SFP 56 gigabits per second can also accommodate 10 gigabits per second module and 28 gigabits per second module. But in order to get the most optimum speed of 56 gigabits per second, we should be plugging in a module that is compatible with 56 gigabits per second. We have different configurations available. We have 1x1, 1x2, 1x3, 1x4, 1x5, 6, and 8. So what do we mean by 1x1 configuration is the one before means the number of rows, and the second number denotes the columns. So on the bottom right side, we can see that there's 1 row and 4 columns. That means that one's a 1x4 configuration cage. And then we have 2x(n) combinations also. So on the top right side, you can see that there are 2 rows and 1 column. So that one is a 2x1 configuration. And we have different 2x(n) combinations available too. So we have 2x1, 2x2, 4, 5, 6, 8, 11, and 12. Then moving on, we have our QSFP. So our quad small form factor pluggable. So this one has 4 high-speed lanes, and this one is same. We have different ganged and stacked options available. So you can see on the left side that the 1x(n) is considered ganged, and 2x(n) configurations are referred to for stacked configurations. We have this available in SMT form factor and also in press fit. And we have multiple different heatsink and light pipe options available, as you can see on the picture. Then we have our QSFP-DD. So QSFP-DD is the doubled density version of a QSFP. So on the top right, if you look at the connector cross-section, you can see that there is an extra layer of wafers. So that is for the double density version. So when we are talking about AI applications, there is a need for more density, and because there is limited space on the front panel, and we need to fit as many lanes as possible in each server so we can process more data and utilize the space efficiently. So that created a need for QSFP-DD. The benefit of QSFP-DD is the backwards compatibility with a QSFP module. So a QSFP module can be plugged in to a QSFP-DD cage and connector. Only the front row would engage, but if we want to take the full utilization of the QSFP-DD connector, then we should be using a QSFP-DD module. The QSFP-DD cage and connector is also designed to handle 12 to 15 watts, which is more than what the QSFP can handle. And we have different configurations available, even for our QSFP-DD. We have 1x1, 1x2, 3, 4, and 5 cage configurations. For stacked combination, we have 2x1 and 2x2. 2 by 2. Then we have our OSFP, which is the octal small form factor pluggable. So OSFP also has 8 lanes, similar to QSFP-DD. So the benefit of designing an OSFP is there is a better thermal performance compared to a QSFP-DD, and it can handle more power. So with higher speeds, there is a need to put more power through the connector, and with more power, there's more heat that's generated, and the heat needs to be dissipated. So OSFP was designed to have a bigger cage, and it has a heatsink on the module, which allows for it to have a better cooling. And therefore, it can handle more power compared to a QSFP-DD. We have OSFP available in different combinations and configurations. We have a 1x1, 1x2, 3, and 4 cage option available. And for stacked options, we have 2x1, by 4, and 2x6. Then we have Mini-SAS HD, which is our PCIe for PCIe application and storage application. So our Mini-SAS HD meets PCIe Gen 5 application spec, and we have it available in 1x1, 1x2, and 1x4 configurations. So now we'll talk about 112 gig cage and connectors that we have available at this time. So starting off with our SFP. So SFP, we have 112 gigs per lane. And since there's one lane, it has an aggregate of 112 gigs. Below is our SI charts. So the SDD is our insertion loss. SDD21 is our insertion loss. SDD11 is the return loss. SCD21 is our mode conversion. And SCC11 is our common mode reflection. So when it comes to high speeds, obviously we need to make sure that there's no crosstalk, there's no loss in data, because we're dealing with a lot of data at really high speeds. Then the signal integrity becomes a really crucial part. So that's a big that's really big for us to make sure that there's no loss in the data. For QSFP, there's 2 different types of footprints that we have. So there is the 0.8 LL version, and we have the 0.6 JL version. They're both they're both MSA standards. We can go more into detail on what's the difference between the 0.8 LL and the 0.6 JL versions. So this one can do 112 gigs per lane. So with a QSFP with 4 high-speed lanes, it can do an aggregate of 400 gigabits per second per connector. We have this available in different heatsink and light pipe options. This is also backwards compatible with a QSFP-28 and QSFP-56 optical transceiver. But as stated before, it's best to use a QSFP 112 gig module with a 112 gig connector to get the best performance. We have all our cage and connectors they're able to do belly to belly. So on the PCB, you can have a cage and connector on the top and the bottom side both. So this helps have a higher density of cage and connectors on one PCB. So the 0.8 LL version. So 0.8 LL was developed by North America, and 0.8 refers to the pitch between the 2 SMT pads. So on the bottom right on the drawing, you can see that the pitch between the 2 pads is 0.8 millimeter. And the LL refers to the shape of the SMT pads. So on the top right, if you see the SMT pads, they're in the shape of an L. So that's why it got the name 0.8 LL. So for this one, we have it available in 1x1 and 1x2 cage configurations. Then we have our 0.6 JL configuration. So 0.6 is the pitch between the two pads, and the JL again refers to the shape of the SMT pad. So on the top picture of the drawing, you can see that the front is in the shape of a J and the back SMT is in the shape of an L. So that's the JL. This was developed by Alibaba, and it's a Chinese MSA standard. We have this cage and connector configuration also available. For this version, we have a 1x1 connector. As for the cage is the same as our QSFP-28 and QSFP-56 cage. For the stacked combination, we have 2x1, 2x2, and 2x4. One thing to note is a lot of effort goes into making sure that our connectors have a good thermal performance. So on the top right side, you can see on the connector, there are channels for air to flow through and cool down the wafers. So with such high speeds, such as 112 gigs per second per lane, there is a lot of power that's being put through these wafers and through our connectors. So in order to make sure that the wafers are being cooled, there's these air pockets and air channels that were created in the connector to help cool down these wafers and make sure that the data is being transmitted without overheating the cage or the connector. Moving on to our QSFP-DD 112 gig. So QSFP-DD, so this is the double density version. So there's a lot of work that was done when we were developing our QSFP-DD 112 gig to minimize the crosstalk between our rows and between row to row. And for this QSFP-DD, we have different configurations available. We have it available in 1x1, 1x2, 1x3, 1x4, and 1x5. We have various different heatsink and light pipe options also available for these. For stacked versions of QSFP-DD, we have this available in 2x1 configuration. And on the bottom right side, again, we can see that there is these air pockets that we have on the front side and on the sides to let the wafers cool down and to pass the air through to make sure that we can put a lot of power through these connectors without them heating. Here's our SI simulation again. So all this I'm showing for our signal integrity is measurement data, and it's not just simulation. So again, it shows our return loss, insertion loss, and our crosstalk between the different wafers and connector. So coming on to OSFP 112 gig. OSFP is again it has 8 high-speed lanes similar to our QSFP-DD. So it has better crosstalk compared to QSFP-DD because there's less number of wafers that are needed. And we have this available in 1x1, 1x2, 1x3, and 4 standard cage, and 1x1 and 1x2 riding heatsink. So when I say a standard cage, there's 2 different types of cages for OSFP 112 gig. So the standard cage is shown on the top side, which has, when you plug in the module has heatsink already on the module. And the height of the cage is higher to allow for the heatsink on the module. Then the other version that we have is the riding heatsink version. So for the riding heatsink is shown on the bottom right side of the picture, where the heatsink is on top of the cage. For this version, there is no heatsink on top of the module, and so it acts like the other configurations that we have for SFP, QSFP, and QDD, where there is no heatsink on the module, but it's a riding heatsink on top of the cage. Here's our SI measurement report. So for insertion loss, return loss, and our crosstalk again. On the top right side, we're showing a picture of the measurement of the board that we use for this measurement. So the green board is the MCB, and the other side is with the Phi SI, that's our HCB. And the way we test it is we'll put the signal through the HCB, it will go through the connector and then through the MCB to a chip, and then it'll make a loop, and we'll see how much loss we are seeing in the channel. OSFP has a lot of thermal performance advantages over the QSFP-DD. So OSFP can handle more power compared to a QSFP-DD. So one thing that allows for it to be better at handling power is because the heatsink is now on the module itself. So it allows for it to have a better cooling. And on the back of the cage, you can see that there's openings to let the air pass through. So for other QSFP-DD and QSFP modules, there's no heatsink on the module itself, and the heatsink is on the cage. So the heat needs to get transferred from the module to the heatsink, where there's some losses, and then from the heatsink, it gets out. So this way is more efficient, as the heat is being dissipated right off of the module, and therefore it can handle more power. We have the OSFP also available in stacked configuration. And on the top, you can also see there's a lot of openings on the connector, and that is to allow for air to pass through and cool down the wafers. We have the stacked available in different configurations in 2x1, 2x4, and 2x6 with multiple different heatsink and light pipe options. So coming to our thermal solution. So thermal is a big part of high-speed I/O connectors. So since we're putting a lot of power through these cage and connector, we need to make sure that we're efficiently cooling these modules and our connectors. So we have different types of heatsink. We have a block style, pin style, fin style, which is front to back, fin style side to side. And we also do a lot of customized heatsink depending on our customer need. So on the top right side, we can see that it has side heatsinks that was developed for a low profile server where there wasn't a lot of space on the top. And then on the bottom right, we can see that it has a top and bottom heatsink both, because the bottom heatsink is to cool down the bottom module. There are some heatsinks you can see in the pin style and the fin style, which are black in color. So that one is anodized. What anodization helps is it creates small pockets on the heatsink itself, which helps it to give more surface area and to help cool down the heatsink faster. We also have zipper fin from front to back. We have zipper fin with embedded heat pipe to transfer the heat and take it out to the back. We have a cold plate interface, a thermal Peltier module, which cools the bottom part and heats up the top part, and then the heat can be lifted off of the module. and we have a plate style and a low profile height with a rear cold plate. So as we're looking at higher speeds of doing 112 gig, a lot of people are looking at doing liquid cooling, and that's where we need a cold plate. So a cold plate helps transfer the heat from the module to a cold plate where it's liquid cooled and takes the heat away from the server, and and the heat is transferred outside. So it's less noisier compared to our conventional air-cooled server storage system. We also developed MicroTIM. So a key advantage of that is that no surface is perfectly flat. So when we have our heatsink, there are small gaps between the heatsink and the module, which are not being utilized. So in order to make sure that the heatsink is making a perfect contact with the module, we can apply MicroTIM coating on it. So right now we have a MicroTIM 1.0 and MicroTIM 2.0 versions. So what MicroTIM allows is it creates a layer between the module and the heatsink, so there is good transfer of heat between the heatsink and the module. On the right side, you can see the readings that we've got. So M to M is metal to metal, and MicroTIM 1.0, MicroTIM 2.0, even with multiple mating cycles. So we can see that if we compare the delta temperature between ambient and the module, it's really high when we're looking at metal to metal. And one thing to note is for all these, the flow rate was kept the same, which is 10 CFM, and the module was putting out 30 watts of power. So we can see that MicroTIM 2.0 performs significantly better than metal to metal or even MicroTIM 1.0. And with multiple cycles, the MicroTIM doesn't lose out on anything, and it's still able to perform really well. We also can do simulation based on our customer needs. So depending on the customer application, they can let us know what's the flow rate they have, how many openings they have on their server, what's the ambient temperature, and we can simulate a design for them and recommend the best heatsink, or if a custom heatsink needs to be designed for their application, we can also assist with that. We use Siemens SimCenter and also ANSYS IcePack to do these simulations and analysis. We also have an wind tunnel thermal test at our facility. So this is to do real life testing, and we have an air velocity sensor, and on the back we have a fan which pulls the air from the front to the back. And on the modules, we have some dummy modules and some active modules. So the active modules put out power similar to how it would in real world scenario. And we can measure, and we have sensors to measure what's the temperature, what's the ambient temperature, what's the temperature on the casing. And we can control the flow rate and make sure that our cage connector, everything's performing to the best. And thank you.
Amazing. Thank you, Karam. And it does look like we have run out of time for the Q&A, but if you do have any questions, please do not hesitate to reach out. Thank you for joining HSIO Connectors and learning more about their latest AI and machine learning design solutions with Karam Siddiqui. We hope you have a great rest of your day.